Okay, so today we're doing a slicing method, and it's to find the volume by a cross-sectional area. So you may remember me discussing before shells how we do either a vertical slicing or a horizontal slicing, and I was talking about what the cross-section would be. It would be like a thin disc or a washer. Showed you what a washer looks like in real life. So it's not always just possibly a disc where it's the area of a circle. Okay, and that's actually what we're using, like pi r squared. It could be other shapes as well. We may stick to just talking about like the simple shapes for a second or two. But you may have even remember talking about cross sections and like pre-calculus. So let's say we're given a package to be sent by mail, and it's a rectangular package like this one, and we need to do the perimeter of the cross section, and that's where you may have already discussed it. So if we were to slice this and it was a square base, then the square is your cross section. And if you know your cross section shape, then you can write the area. All right, so I'm very poorly writing a cross-section shape. Okay, so let's write this first one. So the area of a square is the size squared. Okay. So you do need to know how to represent the measurement for a side. Looking at its graph later on, but your main thing is to understand what the area is. Let me try to erase this. Okay, so circles we already discussed. So we need pi r squared. Sometimes they talk about the diameter instead of the radius. So since the diameter is 2 times the radius, then you can just say that the area is pi times d over 2 squared, and that will simplify to be pi over 4 d squared. So sometimes, hey, they are pretty like straightforward, and other times we're going to need to like figure them out a little bit further. So it depends on the problem. Okay. Semicircles, so that'd be half pi r squared, or we would have to half this if they mentioned the diameter instead. Circles, semicircles, squares. Okay. Equilateral triangles or triangles. I said equilateral so that you could possibly like find out what the height is, because you know the area of a triangle is 1/2 base times height. So you may be able to measure out the base between a function and an axis or something like that, but then well, what about the height? So if you look at an equilateral triangle, okay, not only are the sides all equal, but the angles are all equal. So if I need to find the height, then I'm actually looking at a 30, 60, 90 triangle. And so I can kind of use that reference. So if I know the base, then this is half the base. And my half is not coming out very well here. And so using our ratio, if this is x, then our height would be x radical 3. So our height would be radical 3 over 2b. So we can plug that in to here, and we can use that for our formula for area. So once again, it may be something you need to like figure out off of something that's pretty simple, but nothing that's too complex that you can't figure out or do. So do know your special right triangles because they do come in handy. So let's take a look at our example here. Let me pull it up as you guys copy down your formulas if you didn't do so. Maybe some of these area formulas if you happen to not know them. And the 4 steps to find the volume by method of slicing. Okay, so 4 steps is 1, sketch the solid and a typical cross section. So basically what we're trying to do is draw out on the coordinate plane our region and then try to make it look 3-dimensional, basically by just drawing a few cross sections. Okay, so I'm going to write the word few here just to remind you guys. Find a formula for a of x. It's possible that it may be a of y, but we're going to stick to a of x for now. And 3, find the limits of integration. So where your region starts and where it ends. It's usually described in the problem somehow. And 4, integrate that to find the volume. So if it's a of x, it's with respect to x. If you do get a problem a of y, then you'd be writing dy. Remember, your limits of integration would be y equals. Alright, so let's take a look at our example. Okay, so we have this example, and to do this example, we're going to 1, sketch the solid in a typical cross section. Okay, sometimes we need to kind of sketch a few in order to kind of show that we do have a solid and it is 3-dimensional. 2, find a formula for a of x, as we're going to focus on today. With the a of x, not a of y, maybe for future problem. 3, find the limits of integration, so where a region starts with an x equals and where it ends with an x equals, as opposed to what its y values are. 4, integrate a of x to find volume, so we're going to be using this formula I've already circled for us up here. So, example. I could copy it down while I'm trying to sketch it out a little bit neat. So the cross sections perpendicular to the x-axis of a horn-shaped solid are circles with diameters running from the curve y equals x to 1/3. That's a common function. You should know what that looks like. To the curve y equals 4/3 x to 1/3. Okay, in the xy plane. The solid extends from the origin to when x is equal to 1. Find the volume. So we have here, okay, our common function. That'll be the first thing of y equals x to 1/3. So it's going through these points as best as I can. Not too bad. So now that's 1/3, 2/3, 3/3. So we have 4/3 here. And if you want, you can like label that 1/3. That would be appropriate because then it would be a graph, or at least have the 1 and the 4/3. So we have like a sketch going on here. And so it also goes through the origin, our next function, and it goes up to 4/3, same sort of curve. Okay? So, now, our region's going from 0 to 1, okay? So you may want to like kind of cut it off, but what's most important is that we're going to try to make across at least one, actually should be a few cross sections among this region. Okay, so this is where it becomes 3-dimensional. Now you may notice in some books, even in maybe our textbook, we'll have this drawn out for us, and it doesn't look as bad as I'm drawing it out, but you can kind of see how a circle is kind of created. Okay, where this would be the diameter, and like the bottom part is like somewhere within like that region. But the diameter is going from 4/3 extra 1/3 function to the extra 1/3 function. Okay? Okay, so next we need a of x, and this is the formula for the circle. And so we want to talk about the diameter. And so we already discussed, hey, it's going to be pi over 4 times the diameter squared. Well, the diameter is measured from 4/3, and I should have left that bigger, so I'm just going to put an arrow. 4/3 extra 1/3 to extra 1/3. So we're just subtracting it to find that diameter. Okay, so that's how we measure it out. So if we do that, okay, this is d sub x, then we can finish off our formula for area. So a of x would end up being pi over 4 times 1/3 x to 1/3 power squared. Okay, do simplify because it'll be easier to integrate this when we have to do that. So I'm going to write this as, okay, once we square it, pi over 36 x to the x to 2/3, because x to 1/3 times x to 1/3, same base, add the exponents, it becomes 2/3. All right, so let's talk about the limits of integration. So we're starting to see these cross sections appear from when x is equal to 0, and it's kind of hard to draw near that. I should have done maybe something a little bit closer when x is equal to 1. So we should be able to do step 4 now. Let's erase the part we really don't need. And we're going to find the volume. So v sub x is going to be the integral from 0 to 1 of pi over 36 x to 2/3 power with respect to x. Okay, so easy to actually find the integral, and hopefully you got this part down. So let me see if I can get rid of this. In the meantime, a little bit went away here. Alright, so let's find our volume. Take out the pi over 36 to kind of help us out. And we end up with needing to plug in 1 and 0 into this expression here. Whoops, that's a 5, by the way. We add 1 and we divide by our new exponent. This is what we get, and we just plug that in. And don't forget to subtract. Well, this is going to be 0 anyway, so it's easy to calculate. So we end up with our volume to be pi over 60. So hopefully the end result shows you that, yeah, the last few steps are just integration. Yes, you do need volume. You do need this expression for the diameter, or if we were using the formula for radius, then have r of x. You do need an expression for that before you go, but you should be good to go. So good luck, have fun, and that's it.